students. Welcome back for our next lesson video as we finish up our notes today talking about fossils. In fact, more specifically, as we speak of fossils today, we're going to be talking about the age of fossils. Now, here's a picture of my father, and so I can expect to look like this when I'm older as well. But, if you look at this gentleman in the picture, you might be able to say something about his age. Do you think he's younger or older than me? And I was just joking about him being my father. This is not my father, but he looks like a nice guy. But do you think he's older or younger than me? And be careful when you answer that question. He's probably a little bit older, although it does appear that I am catching up to this individual in this picture. But looking at different people, we have the ability to tell whether one is older or younger than the other. And it's pretty straightforward when we do that. If you have brothers or sisters, uncles and aunts, fathers and mothers, babies at home, you can look at a family picture and pretty much tell other people who's older, who's younger, or even someone outside of your family could say who's older, who's younger, just by looking at the picture. This is one way that scientists can determine the age of fossils, and it's called the relative age. You see, we're going to be talking about two different kinds of ages of fossils today. The first one is relative age. This is pretty straightforward. And when scientists determine relative age, what they are doing, just like the examples I gave of different members of a family, all they're doing is determining the age of a fossil relative or compared to another fossil. So it says absolutely nothing about exactly how old that fossil is. That's not what we're talking about when we are considering relative age. Like if we look at this picture here we have a baby, here we have an old geezer like me. In comparing these two individuals, hopefully it's pretty obvious to you which one of these individuals is older and which one is younger. Obviously, this dude is older, this individual is younger. Now, we have no idea of their exact age, but that's not what relative age is all about. It's just comparing ages. Now, there's a law in geology that helps us take this a little step further. When we're talking about relative ages of fossils, as well as of rocks for that matter, we need to refer to something called the law of superposition. And the law of superposition simply states that in sedimentary rock layers, and if you look at the layers here, this would be an example of layers of a sedimentary rock. In sedimentary rock layers, the older rocks are beneath younger ones. So if you look at this diagram, we can see that layer 1 is at the bottom, layer 4 is at the top, and we can see the labels that layer 1 is the oldest, layer 4 is the youngest. But let's see if we can understand this a little bit better. Imagine you were playing tackle football with your friends, okay? And you are the one with the ball. What is everybody else on the other team going to try and do? They're going to try and tackle you, right? They're going to try and get you down on the ground. In fact, if the other team succeeds at tackling you, you will be the first one on the ground with the ball. There might be a player from the other team on top of you. Maybe another member from the other team on top of them, and so on. Point here is this. You would be the first one to make contact with the ground. you would be on the ground longer than anyone else that landed on top of you. That's kind of the idea with the law of superposition. The layer that was laid down first is the oldest one. Here's another example. Think about making a layered cake. Ooh, yum, yum. If you're making a layered cake and you make the different cake layers, you bake them separately, and then you start putting them together. Well, you're going to have to start with a layer that's going to go on the bottom. Now, if you had a stopwatch and you were timing when you began making your layered cake, the layer on the bottom, before you add the yummy icing or treats or whatever between the next layer and the layer on top of that, the layer that's been down there the longest is the one that you put down first. The youngest one is the last layer that you would have put down. So, bottom line is the law of superposition recognizes the fact that in nature, if you're looking at layers of sedimentary rocks, it's logical, it stands to reason that the one that's on the bottom is older than the one on the top. So hopefully you get a feel for how the law of superposition works. Now let's take this a step further, thinking about things that might be in rocks. Let's say we've got fossils that are in those rocks. If we've got fossils in layers down below compared to fossils that are up above, what could you say, relatively speaking, about their ages? All that you could say is that the one on the top is younger than the one on the bottom, which is older. You can't say exactly how old they are, but relative to one another, you can say that the one down further is older than the one up top. That's the idea of the law of superposition. Here's another illustration to show this. Again, youngest layers are on the top of a column of sedimentary rocks, but let me quiz you here. Looking at the diagram on the right, we've got fossils A, B, C, and D found in 4 different rock layers, layers 1, 2, 3, and 4. Thinking about the law of superposition, can you tell me, fossil A, B, C, or D, which one is the youngest and which one is the oldest? If you said that the youngest is A and the oldest is D, you're absolutely correct. And you can see how those layers correspond to the law of superposition. Because here's the deal. Fossils that are found in sedimentary rocks, again, it stands to logic and reasoning that these fossils were formed at the same time as the sedimentary rock layer was formed. And so the age of these fossils are probably pretty close in age to the age of the sedimentary rocks that they exist in. Which brings us to the next point. There's something geologists call index fossils. Index fossils are layers of rocks with fossils in them that are close in age to other layers with the same kind of fossils. That sounds like a bunch of gobbledygook right now. Let me read it again. Index fossils. Layers of rock with index fossils are close in age to other layers with the same kind of fossils. Now, as you're writing this down, let me say that it's going to become a lot clearer to you with the next picture that I show you. All right, the next couple pictures, in fact, that I show you. Because index fossils, in fact, I'm just going to change the order of some of my slides here. Don't worry, I'm coming back. There we go. I'll give you another moment to copy that down. Actually, you know what? I'm going to take that back. I'm going to put it back to the way it was. I liked it back the way it was. All right. So, again, layers of rock with index fossils are close in age to other layers with the same kind of fossils. This is what geologists do when they start comparing different regions of the planet. Let me illustrate. Here's a diagram which utilizes index fossils. As we're going to learn in geology this year, we're going to be learning that sedimentary rock layers are laid down pretty much horizontally on planet Earth. But there are various factors due to plate tectonics and forces moving these layers around. Sometimes the layers will be shifted, they'll be tilted diagonally, maybe even sometimes totally bowed up. We're going to be talking about things called anticlines and synclines when we talk about geomorphology later this unit. And we're going to see how the land itself can change its shape. But when you look at the type of rocks, even in two different areas, if it's the same kind of rock that has a particular type of fossil in it, you can probably conclude that those different rock layers are of the same age. So let me take it again a little step further. Let's say we have a fossil over on this side of a canyon or a valley, and we'll call it fossil number 1, fossil number 2, fossil number 3, whatever those fossils might be. Now, if you look directly across the valley, and we see the kinds of fossils that are found over on this side of the valley, they're not completely horizontal to one another. Instead, we've got fossil 1 way up here, fossil 2 and fossil 3. They're not directly opposite one another. Well, if we were to cut a cross section into this valley or this canyon, we would probably see that the sedimentary rock layers have been tilted or uplifted for some tectonic reason. But the deal with index fossils suggests that if you find a particular type of fossil here and the same kind of fossil over here, these fossils are probably of the same age, and the rock layers are probably of the same age. So let's look at a more detailed example here. Like people studying the Grand Canyon, for instance, or other canyons, might be looking at two different sides of canyon walls. And they might find a number of fossils that exist on both sides of the canyon walls. If they find the same kind of fossil here as they do here, you might conclude that these rock layers existed around the same period of time because these fossils are probably of about the same age. That's the whole idea that we're trying to get across here with index fossils. And in addition, we can also state, due to the law of superposition, that this fossil here is going to be younger than the fossil underneath it, which is younger than the fossil underneath it. And when we start comparing these index fossils to index fossils elsewhere in the world, if we find fossils here that don't exist here, at least we can speculate and conclude that maybe these fossils are relatively younger than these and older than these. Again, index fossils, relative fossils, they kind of work hand in hand. But now let's get to the second major kind of aging of fossils, because this is rather interesting, and it is the absolute age. It's going to take us a little bit longer to talk about absolute age because it can get pretty technical. If I were to ask you how old you were, you would probably tell me how many years old you were, and that's based on your birth date. If you know when your birth date is, that you probably celebrate every birthday that you have, every year that you're alive, you count back from your birth date, no matter what that is, and you know how old you are. Or rather, you know how old you are because you know what day you were born. And of course, you're probably just taking your parents' word for it because I highly doubt any of you remember exactly what day you were born. But I am very sure, as a parent myself, I'm very sure that your parents know exactly what day you were born because they probably remember it very vividly. But knowing your birth date, you can calculate how old you are. But you need a starting point. You need a starting point. So let's talk more about fossils and absolute age. You see, scientists, geologists in particular, are getting better and better at calculating and determining what we call the absolute age of fossils. And we describe absolute age as determining the actual age of a fossil. Now, when we say that, we're not exactly talking about a precise birth date, on a given day of a given year, at a specific time, like we know our own absolute ages. But absolute age with fossils can narrow down the actual age of a fossil much more precisely than just looking at relative age. Let's go further here. It is based on what is called radioactive dating. What is that? Well, radioactive dating utilizes radioactive elements and the knowledge that they decay at a constant rate. If I were to show you an hourglass, and I'll show you one in class, an hourglass, one of those sand timers, it's got sand on the top, sand on the bottom, not unlike this illustration right here in shape. As soon as you flip that over, the sand starts falling out. And if you could count the number of grains of sand coming out and you compare it with a clock, you could probably come up with a very good measure of time and the passage of time. Like maybe in a particular hourglass, 60 grains of sand every second fall through the opening. And if you could count the number of grains, you could predict how long ago that hourglass was turned over by counting the number of grains of sand. Does it sound tedious? Yeah. Would it be mathematically possible? Absolutely. It would just take a while to count all of those grains of sand. But hopefully you get the idea. Because you see, here's the deal. We have found that there are certain elements in the universe. There are certain elements on planet Earth. And excuse me one moment. I'm back. I just had to turn the radio down. So there are certain elements in the universe that are radioactive. What does that mean? Well, radioactive elements decay, they fall apart. It's like grains of sand falling through an hourglass, and they do that at a constant rate. And there's something in science called half life. Half life is described as the amount of time that it takes for one half of an element to decay. Now, when we're in 8th grade, we're going to learn a lot more about radioactivity and we'll unpack this and you'll understand this a lot better. But for now, just think of the hourglass example. You flip an hourglass upside down. When half of those grains of sand fall through, that's the half-life of that hourglass. In fact, you could probably tell me what the half-life of an hourglass is. If an hourglass takes an hour for all of the sand to drain out the hole, how long would it take for half of those grains of sand to fall through the hole? Hopefully you're thinking a half hour or 30 minutes. Now, when we talk about elements, there are some really well studied elements like carbon, a particular isotope of carbon called carbon 14, potassium and argon, which decay at measurable rates. And so we use these kinds of elements to help us identify the actual age or the absolute age of fossils. Because here's the deal, let's say a sample of a rock or a fossil in a rock contains a certain amount of a radioactive element, like potassium, a certain isotope of potassium. We know through experimentation that potassium decays like an hourglass loses its grain of sand at a regular rate. Now, that flipping of the hourglass basically starts at the time that that organism dies or that the rock is laid down and is buried by other rocks. So if we uncover a fossil, or if we excavate a rock, and we study how much of those grains of sand are left, we can basically, through calculations, just like that hourglass and the grains of sand, count back and determine when it was flipped over in the first place. We can measure the passage of time through the use of radioactive elements using this idea of half life and radioactive decay. That's all we need to know for now. The difference between absolute dating and relative dating. Again, we're going to learn a lot more about this process when we get to nuclear chemistry in 8th grade. So we're going to finish with just a quick comparison of absolute or radioactive dating and relative dating. Here are some of the biggest differences. Both of them can tell you something about the age of fossils. Relative dating, you can do it in the field. You can just look at rock layers and determine, well, these fossils are below other fossils, they must be older. We're just comparing fossils to determine which ones are older. Radioactive dating, on the other hand, absolute dating, has to be done in a laboratory with really high-tech specific equipment to determine. It's measurable in the lab. In more basic terms for our notes, they both determine age. Relative dating can be done in the field. Radioactive dating is done in the lab. Now, tomorrow we're going to be examining actual fossils. Now, we're not going to be examining in their natural environment, so we can't really use the relative dating methods. We could use other resources to examine index fossils, perhaps, and we can also use information that I have gathered regarding the radioactive or the absolute dating of the fossils that have been performed in the laboratory. But we're not going to be really focused on determining the age of fossils in the lab tomorrow, but rather we're going to be observing fossils, and you are going to try to identify the type of fossil that it is. So I'll keep you in suspense until tomorrow, for tomorrow is another day. But for now, I'm going to say bye bye.